The following presentation is about the extension of a graph similarity method that supports graph with not known node correspondence called NetSimile. Surprisingly, although there is a growing interest of the usage of graph-based recommendations for information, they're not good enough measures that can compute the similarity between two arbitrary graphs and provide an optimal result based on the resemblance of the graphs. The rapid increase of information posed several issues in terms of introducing metrics exposing the correlation of two graphs. Consequently, graph matching is a broad research area covering different concepts of similarity. An emerging problem is that different graphs need to be applied different similarity metrics to expose their similarity. Considering a series of graphs of various sizes, a critical problem is mapping of nodes between graphs based on both the similarity between the nodes and also the topological similarity between the graphs. In conjunction with the fact that a node in a graph may have multiple similar nodes in other graphs, it is challenging to implement a measure that calculates the similarity between nodes, taking into account different structural notions. Therefore, the area of computing a quantitative similarity measure between graphs with not known node correspondence is not explored enough. Before we explore in depth the project, let's say in brief some terminology. Throughout this presentation, a graph G is defined as a triplet: vertices, edges, and labels, where two vertices of the graph may be connected with an edge. Each vertex or edge may be labeled. In this presentation, we are only interested in undirected graphs. By the term known node correspondence, we simply mean the case of two undirected labeled graphs where their vertices have one-one mapping. The vertex and edge sets of the graphs may or may not have the same magnitude. Every vertex from the first graph's vertex set is checked if there is a single vertex from the second graph's vertex set that is mapped to it, or no vertex at all. If a mapping exists, then the node correspondence is known, otherwise is not. The node correspondence can be predefined or computed. Despite the fact that this is such a difficult procedure, many scientists try to tackle this problem. One method that implements this is the eigenvalue method proposed by Kutra et al. The authors of this method are approaching the problem using the eigenvalues of each graph. In particular, considering the Laplacians of the graphs, the similarity between the graphs is computed by calculating the eigenvalues of the Laplacians with the equation displayed on the screen. High scores are associated to dissimilar graphs, and low scores are assigned to similar ones. However, this method is not ideal for disconnected graphs, since it only captures local structural differences, and furthermore, the graphs are only locally compared. The central goal of this project is to solve the problem of computing the similarity between two graphs with not known node correspondence by extending and comparing two well-established graph similarity methods. When it comes to graph similarity, there are two proposed approaches, deltacon and NetSimile. Currently, deltacon is considered to be the state-of-the-art method for computing a similarity between graphs with predefined node correspondence using structural differences. Conversely, NetSimile is not as advanced and fast as deltacon, but it supports graphs with not known correspondence using feature extraction. In this work, we have extended deltacon to deltacon++ in order to support node weights and graphs with computed node correspondence. Furthermore, we have extended NetSimile to NetSimile++ in order to support node and edge weights. And lastly, we have extended both of the methods in order to support node and edge labels. Finally, after transforming the methods in directly comparable versions, we provide a method-by-method comparison, recording the effectiveness and efficiency of them. We intend to prove that the extended version of NetSimile provides more discriminative results. In the following slides, I will describe in brief the methods. To begin with, deltacon is focused on finding similarities between networks. It takes in account the structural properties of each graph. For instance, delta con weights more changes that make a graph disconnected or changes to less dense graphs than changes to much denser ones. The process goes as follows. It first computes a pairwise affinities of the nodes of each graph using fast belief propagation, which are stored in matrices. The affinities of the nodes are then used to compute the distance of the graphs using root Euclidean distance, which is converted to be bounded in 0 to 1 included. The authors have set 4 properties to delta con. The first is edge importance, where changes that make a graph disconnected or changes to less dense graphs than changes to much denser ones are weighted more. The second is weight awareness, where the importance is higher of the absence of an edge with higher weight than the absence of an edge with a smaller one. Third, we have edge submodularity, where if we given two constant size graphs, where the magnitude of the edge set of the first graph is smaller than the magnitude of the edge set of the second graph, changes to the edges of the first graph are more important than changes to the edges of the second. And lastly, we have focus awareness, where targeted changes are penalized more. If a series of edges are removed in a targeted way, then the similarity score is smaller than if the same removals were done in a random one. NetSimile is a graph similarity method that supports graphs with not known node correspondence. NetSimile meets 3 properties. First, the similarity scores obtained are size invariant. Second, the node correspondence problem is avoided. And third, it is scalable with linear runtime complexity on respect to the number of edges. In order to be succeeded, the algorithm has 3 steps. First, feature extraction. Second, feature aggregation. And third, similarity comparison. Figure on the screen demonstrates the 3-step process performed to produce a similarity score. Consider a graph G. The step 1, feature extraction, obtains 7 features including the eigenvalues and the degree from each node, creating an n times f feature matrix for each graph, where n is the number of nodes in a graph and f is the number of features. Step 2, feature aggregation, which applies 5 different aggregators to the feature matrix, creates a unique signature for each graph, which is a one-dimensional vector with 35 values. Finally, step 3, similarity comparison, uses Canberra distance to calculate the distance between the 2 graphs and produces a final similarity score. The authors introduced many distance metrics that can be used to compute step 3, such as cosine distance, but Canberra distance was chosen because it is a very sensitive metric when it comes to changes close to 0. NetSimile was missing very important features. For instance, label-aware similarity metrics improve significantly the quality of the outputted result due to the fact that they carry rich semantics. Collecting and comparing the labels of each node exposes valuable information regarding the similarity between graphs. Another important feature that is missing is a node and edge weight awareness. Weight-aware similarity metrics can be beneficial too for the improvement of the results. Node or edge weight highlights the importance of that item, and it can serve as an important feature. The absence of a node or edge with a higher weight must be in a greatest importance than the absence of another with a lower. Consequently, we have revisited NetSimile in order to include these important features. Finally, we have decided to use cosine distance for the computation of the distance between the signatures, since the distance that is supported by all of the methods used in this project, providing comparative results. Here is a similar figure as the one above, which we will use to explain the node and edge weight support. To begin with, NetSimile extracts 7 different features on step 1, feature extraction. On this step, NetSimile++ extracts 2 additional features, node and edge weight. A useful point to stress here is that in our implementation, the graphs are created with the help of a Python library called NetworkX. Thus, node weight extraction was a simple function call. Contrarily, edge weight extraction was more challenging. For each node, the total number of weights from all the adjacent edges was collected. The result had to be normalized in order to be within a comparable range. Thus, all the results were divided with the total number of edge weights of all the edges that are adjacent to the nodes. Step 2, feature aggregation, remained attached, and finally step 3, similarity comparison, was done using cosine distance. In order of feature extraction approach to become label aware, another process is also performed in parallel. The process starts by creating a dictionary that reports the number of times that every label exists in the graph. Then the dictionaries of both the graphs are inserted as an input in which their cosine similarity is computed. Finally, the outputs are combined using a lambda. Depending on the availability of the data, the value of lambda is different. For instance, if only the node labels are provided, the value of lambda is 0.6. In any case, higher weight is assigned to the result computed between the two signatures. As mentioned above, DeltaCon was also extended to support node weights and node and edge labels. The extension of node weight will be extended below, and the methods used for computing the node and edge labels, it's exactly the same as the one used in NetSimile++. The root Euclidean distance was also switched to cosine distance for the same reasons discussed as the previous slide. Originally, DeltaCon only supports graphs with predefined node correspondence. We have revisited the method in order to support graphs with computed node correspondence too. To begin with, a wrapper was created which transformed the graphs to the appropriate format supported by the method without affecting the similarity score. A thorough literature review proved that maximum common subgraph was the most suitable method for identifying and one-one mapping between the graphs. The resulting graphs have to have the same number of vertices. Any possible addition of a vertex must be added as a disconnected one. Two different algorithms are added to the collection for computing the maximum common subgraph. The first one is MC split, and the second is a maximum click. MC split is computing the maximum common induced subgraph, which returns the maximum number of common nodes along with all the edges connecting them. This algorithm is taken as an input unlabeled, undirected, and without loops graphs. Throughout its execution, the algorithm is created relating the two graphs using depth-first search. Initially, the mapping is empty. Throughout the process, if pairs of vertices relating the two graphs do exist, are added to the mapping. The second algorithm that was added to the collection is a computation of the maximum common subgraph using the maximum click. This algorithm is following a two-step process. The first step is the construction of the modular product graph between the two graphs. The vertex set of the result is a Cartesian product of the vertices of the two graphs. The second step is to compute the maximum click of the modular product graph. The result of this computation is a maximum common subgraph between the two graphs. Now, having the mapping using any of the two algorithms is an assumption which is justified with testing that the nodes contained in the maximum common subgraph are the only nodes that are similar between the two graphs, and any other nodes are completely different. The process performed next can be explained with an illustrative example. Consider two graphs G and H respectively in the figure. An execution of the maximum common subgraph algorithm will return the mapping of the nodes A to A and B to B. Thus, node C has no relation with graph H and node D has no relation with graph G. In order to transform these graphs to graphs with computed node correspondence, any node from graph G that does not exist in graph H is added as a disconnected node, and similarly, any node from graph H that does not exist in graph G is added as a disconnected one. Note here that the newly added nodes are preserving their features such as node labels, node weights, etc. In the case of a graph G being a subgraph of graph H, no new nodes will be added to graph H or otherwise. Whereas in any other case, both graphs G and H will receive a larger vertex set than the original. The new vertex set will not affect the similarity scores, and they can now be added to delta con as described above. DeltaCon has two main methods. The first one is a calculation of the fast belief propagation of each graph, and the second is a computation of the root Euclidean distance for the final result. The modification for computing the node weights was done in fast belief propagation. The formula for computing it, as proposed by the authors of DeltaCon, is the first formula on the screen, where S is the affinity matrix. Each row I represents the influence of a node I on node G. From here, we notice that if each row I is multiplied by the weight of node I, we achieve the insertion of node weights in the algorithm. In brief, affinity matrix S is multiplied with the diagonal matrix W, where the value at position WII is the weight of node I, as shown in the formula on the second formula on our screen. The resulted equation does not normalize the results. The work done was focused on creating an adaptable extension of fast belief propagation. Thus, even though we have chosen to use cosine distance, we decided to normalize the result in order to be supported by root Euclidean distance 2, which was the author's primary choice. Consequently, the affinity matrix S is divided by the largest node weight in the dataset so that the result is constrained by the range of 0 to 1. Once the scalar norm parameter has been acquired to the final version of fast belief propagation becomes as the third equation on our screen. The evaluation is looking to address the following questions. Which method is the fastest? Are node and edge weights significantly affecting the execution time? Are node and edge weights significantly increasing or decreasing the similarity score? Are node and node labels significantly affecting the execution time? Are node and edge labels significantly increasing or decreasing the similarity score? The datasets used on the experiments were created using a larger real network of co-authorships between scientists posting preprints on the Astrophysics ePrint archive. The network is equipped with node labels and node and edge weights. We have extracted 100 ECONET graphs with predefined node correspondence and 100 ECONET graphs with not node correspondence. We have randomly chosen 20 on each dataset. On the first dataset, named dataset 1, all the graphs have 600 nodes, and on the second dataset, named dataset 2, the number of nodes on each graph ranges from 300 to 1500. We compare NetSimile++ with NetSimile, DeltaCon, DeltaCon++. We chose to compare extended NetSimile not only with the extended DeltaCon, but also with our original versions in order to study if there's a downgrade on the speed and if this penalty is in favor of significantly more accurate results. The table on the screen demonstrates the properties supported by NetSimile++ itself and the baseline methods used. As you can observe, only NetSimile++ supports all the properties. The experiments were applied to both of the datasets and covered 4 different aspects: structure, weight, labels, and weights and labels. Each experiment was repeated exactly 5 times in order to compute the standard deviation of the results. Note here that on the experiments that the method was only focusing on one of its features, example NetSimile used on weight experiment, the rest of the supported features were temporarily disabled. Every round produced 3 different results. First, a silhouette score of the dataset. Second, an execution time. And third, a heat map of the distance matrix displaying analytically the distance between each of the graphs. In total, 120 runs were executed. The graphs were clustered using agglomerative clustering, which is a bottom-up hierarchical clustering method. This was done in order to group the graphs together and label them. In order to choose the appropriate number of clusters, each dataset silhouette score was used with a measure that shows the tightness of the clusters. Silhouette score is bounded in -1 to 1, where 1 is indicating that the clusters are as tight as possible, and -1 the opposite. 0 indicates that overlapping clusters exist. Tweaking the number of labels showed us which number produced the highest score, thus the tightness of the clusters, and was subsequently used to all of our experiments on each dataset. As mentioned, each experiment was performed 5 times in order to compute the sample standard deviation of the execution time using the equation shown here. Another point of comparison is the statistical significance of the execution time between NetSimile and NetSimile++. For this, p-value is used to record the difference. A hypothesis is raised that the penalty in execution time is statistically important. Thus, NetSimile++ is significantly more complex than NetSimile. This is a null hypothesis. The alternative hypothesis is to prove that this statement is untrue. In order to justify objectives 3 and 5, the variance and every distance matrix was calculated. This metric was used in order to show how far the results are spread out. The bigger the result, the more discriminative our results are. By definition, variance is the average of the squared differences from the mean. Back to the objectives, DeltaCon was indeed the winner in terms of speed. We can observe that NetSimile++ had a time penalty on every possible case, as expected, but the results were more distinctive on all of the possible datasets. For the sake of brevity, only 4 out of the 24 heat maps generated and interpreted will be demonstrated here. On this slide, we can see that the heat maps of NetSimile and NetSimile++ with node and edge weights and node and edge labels of both of the datasets, since it is the focus of the project. In both of our sets of heat maps, we can clearly observe that the results are more discriminative in the second column of where our extensions are added. NetSimile++ managed to outshine NetSimile, providing results with more valuable insights on both dataset 1 and dataset 2. The first table shows the variance for every distance matrix computed for this project. Every version of DeltaCon++ has a higher variance than DeltaCon. A similar case holds for NetSimile++ against NetSimile on dataset 1. Even though NetSimile++ and weighted NetSimile++ produce a lower variance than NetSimile on dataset 2, the absence of colors in the figure of NetSimile in the previous slide and the plethora of them on NetSimile++ clearly demonstrates that NetSimile assigned 0 distance to many combinations of graphs that NetSimile++ managed to identify differences. As a result, we can conclude with confidence to the fact that our extensions do provide more qualitative results that can identify the similarities and dissimilarities of the graphs in more detail. On the second table, we can see p-value that was used to evaluate whether the penalty on the execution time was statistically significant. Therefore, statistical significance was reported between the execution times on NetSimile and NetSimile++ on both datasets. The second table reports the result. The first column shows that the p-value on dataset 1 is 0.04. The result is not significant at p less than 0.05, thus null hypothesis is rejected. The second column shows that the p-value on dataset 2 is 0.19. The result is significant at p less than 0.05. Thus, the null hypothesis fell just short of statistical significance. As we can observe, the more complex the dataset is, the greater the difference of the execution time gets. This result is expected since there is plenty of added functionality that consumes resources. To conclude, this presentation showed the strengths and weaknesses of two well-established graph similarity methods, DeltaCon and NetSimile. Both of the methods were extended in order to support weights and labels. Subsequently, a formal comparison was made of NetSimile++ against DeltaCon, DeltaCon++, and NetSimile in order to research whether a method can produce more accurate results than the current state-of-the-art DeltaCon, its extended version, and the original version of the method itself. We have collected various statistics that justified our claims that NetSimile++ produces more discriminative results. Generally, our extension reported greater execution time in comparison with all of the other methods, but better performance, showing its ability to expose future differences and variations. All in all, the results were satisfying. Finally, this work highlights the need of a method that can compute the similarity metric between graphs with not known correspondence, since the scientists tend to avoid implementing methods that support datasets of this nature. NetSimile++ provides a scalable and adaptable method that can successfully and accurately compute the similarity between graphs with not known correspondence.